Okay. Our lesson this time is on calculating statistical probabilities. We're going to, this is the last lesson in this chapter, and at the very end we get into a section that is something like math heavy, which can be intimidating to some. I know that I'm not real excited about serious math problems, but these are not super hard, and it is useful to know how to calculate probabilities, because very often we have to make decisions based on statistical probabilities of things. Now, sometimes this is very easy, right? So, for example, sometimes we hear on the Weather Channel that there's an 80% chance of rain tomorrow, and it's very easy for us to conclude that we should probably postpone that picnic that we were going to have, right? So some decisions based on statistics or probabilities are fairly simple to make, not that big of a deal, but sometimes we have to make decisions, or we need to understand things based on probabilities that are a little bit more complex, and it's generally because there's more than one factor or more than one probability to take into account. And in those sorts of cases, we need to know how to think about them and how not to think about them. So this section is about that. So the first type that we need to really look at is called a joint occurrence of independent events. And here's what we mean. That's when there are two events that we want to calculate the probability of occurring together. But the odds of each event are independent of the other, so that one event has no bearing on the other event. They are two independent events that do not operate on or do not connect probabilistically to each other. So here's the definition. Two or more events are independent when the outcome of one has no effect on the outcome of the other. Now, what are examples of this? Well, if I take a single six-sided dice and I roll it once, the odds that I'll get any number is 1 in 6. The odds if I roll it again that I'll get the same number I got the first time, where I get doubles essentially, right? Where I roll, let's say, a 6 the first time and then I roll the second time. When I go to roll the second time, what's the odds that I'll get a 6? Well, the odds are 1 in 6. It's the same odds that I would have gotten a 6 in the first place. Now, the odds that you'll roll two 6s in succession together are much less, but the odds that you will roll a 6 and then another 6, which are independent events, are the same. Each independent event is the same, right? So roll 1, the odds I'll get a 6 are 1 in 6. Roll 2, the odds I'll get a 6 are 1 in 6. Now, those two events are independent of one another. That is, the odds that I'll roll a 6 the second time do not go up or down because I rolled a 6 the first time. They are completely independent events. That's what we're focusing on here. So here's another example. When a coin is flipped twice in succession, how the first flip comes up has no effect on how the second flip comes up. In the same way, whether OSU wins their game Saturday has no effect on whether OU wins their game Saturday. The two are independent events. They have nothing to do with one another. So where events are independent, but one believes that one does affect the other, so where we think that whether or not OSU wins has some sort of impact on whether OU wins, or whether we think that a coin flip the first time has an impact on the coin flip the second time, or where we think that the number we roll on the dice the first time impacts the odds that we'll get the same number or a different number on the second turn, we commit what's called the gambler's fallacy. Okay? So They are independent events, and when we fail to treat them as independent events, that's when we commit the gambler's fallacy. Now, how do we calculate the probability of multiple independent events? For example, what are the odds that I will roll snake eyes? So I've got 2 dice and I'm going to roll them. What's the probability of getting a 1 and a 1? Now, the odds that you'll get a 1 on a single dice are 1 in 6. The odds that you'll get a 1 on the second dice are 1 in 6. But the odds of getting both at the same time, calculating the 2 independent events at the same time, is done a little bit differently. It's not 1 in 6. The odds are a little bit different. So the probability of, let's get into this here. What we want to do is express the probability of each event as a decimal between 1 and 0, or 0 and 1. What we mean by that is, what are the odds that you'll get a 1 when you roll the dice? Well, it's 1 in 6, but rather than saying 1 in 6, we want to express that as a decimal point. So we're going to divide 1 by 6 to get a decimal point. That's going to be the probability. Take, for example, a coin flip. If we do a coin flip, what are the odds? Well, it's 1 in 2, but we're really going to say 50%, or 0.5. The probability that you will either get heads or tails is 0.5. Okay? Then what we're going to do, since let's say we're rolling, that we're flipping a coin and we want to get heads twice in a row. What are the odds that that will happen? Well, the odds that we'll get heads the first time is 0.5, and the odds that we'll get heads the second time is 0.5. So then the odds that we will get heads both times is done by multiplying the odds of each independent event. So if each independent event is at 0.5, we multiply 0.5 times 0.5, and that gives us the probability of getting heads for both rolls, which 0.5 times 0.5 gives you 0.25, or there is a 25% chance that you will get heads 2 times. Okay? So here's the example. Our chance of flipping heads is 0.5. Our chance of flipping heads a second time, because they are independent events, is also 0.5. So if we want to know the odds of flipping heads 2 times in a row, we multiply each instance, each independent event, times another, which gives us 0.25. If we wanted to know the probability of getting it 3 times in a row, we just continue the process. The first time it's 0.5, the second time it's 0.5, and the third time it's 0.5, because again, they are independent events. So the odds that you will flip heads 3 times in a row is 0.5 times 0.5 times 0.5. So what's 0.25 times 5? I don't even know. Is it 1? It's 0.125, I think it might be. Something like that. I think it's 0.125. 0.125. I think it's a 5 times 5. 25 is 125, so it's going to be it should be 0.125. So 12.5% chance that you'll get heads 3 times in a row. Now, something to keep in mind here, and this is important, is that the odds that you'll get heads, heads, and heads is the same as the odds that you'll get heads, heads, tails, and the same that you'll get tails, tails, tails. If you pick any combination of heads and tails, the odds that you will get that combination, let's say it's 2 flips of the coin, and we want to know the odds that you'll get tails, heads. Well, tails is 0.5 and heads is 0.5, so first flip and second flip multiplied by each other, the odds that you will get heads, tails is exactly the same as you're getting heads, heads. Your odds of getting any particular combination of 3 independent events is going to be the same. So it doesn't change just because it's heads 3 times in a row. That's not less plausible, or less probable, I should say. then heads, heads, tails, or heads, tails, heads, or tails, heads, tails. I messed that up. The odds are all the same, and we know that because we can just flat out calculate the probability. If we were looking for tails, heads, tails, that's 0.5 times 0.5 times 0.5. The probabilities don't change. Okay? All right, the next one we're looking at is called alternative occurrences. And this is the, what we want to know here are the odds that 2 or 3 of possible alternatives will happen, not just one. So this is where, rather than just one alternative, right? If I've got a dice, a 6-sided dice, and I roll it, what are the odds that I'll get not a 1, but a 1 or a 3, or a 6 and a 2, right? There I've got alternate, we call this alternate occurrences. What we're really saying is that there are 2 or 3 or more than one possible alternative that we're looking for. So how do we do that? Well, in the last one we multiplied. In this one we just add. Okay, so this is again what we're talking about here is a case where we're interested in whether either of 2 alternatives is going to occur. That is, there's more than 2 alternatives, right? There's 3, 4, 5, 6, 7, 8 alternatives, and we know the probability. We want to know the probability that 2 or more will happen. If you play a certain dice game, for example, one of the dice-based game that I have played with friends of mine and that we had enjoyed particularly in our youth was a game called Axis and Allies. And in Axis and Allies, you have it's kind of like Risk, except that you have specific pieces that do specific things. So you have tanks, and you have infantry, and you have artillery, and you have fighters, and you have bombers, and you're basically in Axis and Allies replaying World War II. And in that game, what's interesting is when you attack with a tank, you can get a hit on an opposing player if you roll a 1, 2, or a 3. An infantryman will defend that attack and take out an opponent by rolling either a 1 or a 2. So what are the odds that I will get a hit, that I will impact my opponent when I'm attacking with a tank? Well, on a 6-sided dice, the alternatives are 1 and 6, 1 and 6, and 1 and 6, but I want to know what are the odds that I'll get a 1, which would get me a hit, and then a 2 that will get me a hit, and a 3 that will get me a hit. Well, it's 1 and 6 for each of them. But in alternate occurrences, I want to know what the odds are of my getting a 1, a 2, or a 3. And if I'm defending and I've got an infantryman, I want to know the odds that I'll get a 1 or a 2. So it's not just a simple 1 and 6 here. There's more possibilities that I'm looking for in my occurrence, what we'll call the occurrence. Okay. To do that, we basically add. Now let's use an example. Let's say, getting away from Axis and Allies, let's say that we're drawing from a 52 card deck. Okay. And when we do that, we want to know the probability that we're going to draw either a spade or a heart. Well, the odd, since the deck is divided into 4 types of cards and there's an equal number of each type of card, assume that we've taken the jokers out. If we're looking for a spade or a heart, not a clubs or a diamond, then we have the odds that we'll get a spade is going to be a 1 in 4, and the odds that we'll get a heart is 1 in 4. The odds that we'll get a spade or a heart is going to then be 1/2 or 0.5 plus, I'm sorry, it's actually 0.25 plus 0.25. So the chances that we'll get a spade or a heart is going to be 0.5. Sorry, I should have put that up on the screen for you. I'm talking ahead of my slides here. The chances that we'll get a spade, because it's 1 out of 4, is 25% chance. The chances that we'll get a heart are also 1 out of 4, so it's a 25% chance. The chance that we'll get either one of them, either one will give us credit here, then is 50% chance. We've got a 0.5 chance that that will happen. Okay? All right. Second to last one here, this is the third of four. We're going to talk about expectation value. Expectation value is a way to determine if the payoff, given its odds, is worth the cost. So, what do we mean by that? Well, sometimes we have to make decisions about whether a certain gain that we receive is worth the potential cost given the odds of our success. Okay? So, I've got examples in here, but in principle that's what we're doing. So when we're calculating expectation value is the amount that we expect to gain combined with the chances that we'll gain it versus the chance that we'll not get it and the cost to not getting it, right? So expectation value, again, is a way to determine if the payoff, given the odds, is really worth the cost. Some expectation values are very easy to determine, right? So if we flip a coin to pay for lunch, what are the odds that it'll come up heads or tails? It's 50-50. And let's assume that like you and I were out to lunch, right? And we each bought a $10 lunch. And we decide at the end of lunch, okay, let's flip a coin to see who pays for the lunches, right? This is clearly going to be a wash, right? Because look, you're trying to save $10 and you're putting up $10, and the odds that you'll save $10 are just as good as your odds of losing $10, right? So you have a 50% chance of paying 20 and a 50% chance of paying nothing. This is very easy to calculate, right? Over the lifetime of our lunches together, let's assume that we decide to get lunch together on a weekly basis for the rest of our lives, and that we both live long and prosperous lives, so that we can afford $20 lunches every now and then. Over our lifetime, if we're flipping a coin for who pays for lunch, and the odds of the coin are 50-50, and you and I are each getting $10 lunches, then the odds that then at the end of the day, you'll win half, you'll lose half, and you'll be no better off, right? I mean, you won't be no better off and no worse off. It'll basically be a stalemate, right, over your life, neither here nor there. Statistically, at least that's the way that it should work out. There'll be some variation, but it should basically work out that way. But see, things get a little bit different when we don't have 50-50 odds and when the payoffs are different, right? So if the odds of my winning are not 50-50, or if the payoffs are different, then the expectation value will be different. And so if we were flipping a coin, but I was spending $5 for lunch and you were spending 15, clearly a bad bet for me, right? Because I've got 50-50 odds, but my gain half the time is going to be way outweighed by the price when I lose the other half of the time. Okay, so it's that sort of thing that we're looking to calculate. Take a different example rather than paying for lunch. Let's talk about the game of craps for a second, right? Craps is a dice game where you bet that when somebody rolls a pair of dice that certain numbers or certain combinations will come up before others and these sorts of things. Okay, so one of the bets that you can place in craps, and this is in your book, so I'm going to describe what's in your book for you here, but one of the bets that you can place is that somebody will roll a 6 before they roll a 7. Okay? Now, let's say, and the way that it works is you put down money that someone will roll a 6 before they roll a 7. And if you win, they'll double your money. If somebody rolls a 6 before a 7, you've put $5 down, they're going to give you $5. But if they roll a 7 before a 6, like if they roll a 3, then nothing happens. But if they roll a 7 before they roll a 6, then guess what? You lose your money. So here what's interesting is that the payoff is the same. It's either +5 or -5, right? You either lose your $5 or you gain $5. So you can turn 5 to 10 or 5 to 0, okay? But the odds that you'll roll a 6 and the odds that you'll roll a 7 are not the same. In fact, more than likely, you will roll a a 7 before a 6. Why? Well, this is all the stuff we've talked about. If we want to find the expected value here, what we need to do is calculate the odds that the different numbers will come up. So I told you that the odds that you'll roll a 6 are worse than the odds that you'll roll a 7. It's actually more likely that you'll roll a 7. How do I know that? Well, because there are more possible combinations of the dice to get a 7 than there are to get a 6. So I've listed them on this slide. What are the ways to get a 6? Well, dice 1 can roll a 1 and dice 2 a 5. 1 can roll a 2 and 2 can roll a 4. They can both roll 3 and the odds of that happening are equal. Dice 1 can roll a 4 and dice 2 can roll a 2, or dice 1 can roll a 5 and dice 2 can roll a 1. But those are essentially 5 different combinations. When it comes to a 7, there are actually 6 different combinations, right? So in each, so what are the odds that a 7 will come up relative to a 6? Well, the odds are better that you're going to get a 7. How much better? Well, the chances of a 7 occurring before a 6 are 6 to 5, right? Because you take the number of possibilities and it's 6 to 5. Since there are 6 combinations that'll get you 7 and 5 that will get you 6, the odds that a 7 will occur before a 6 are 6 to 5, or about 55%. 0.55. Now, if you win, by the way, so then what are the odds that you'll roll a 6 before a 7? Well, they're going to be the converse. Rather than 55%, it's going to be 45%. Okay? So now, how do we determine our expected value? Well, you've got to take what you win and multiply it times the odds of winning it. And then what you lose and multiply it by the odds of losing that. So if you win $5, right? And which is great, but what are the odds that you'll win it? Well, it's just under half. It's 45% chance that you'll win it. Your odds are 0.45. Your expected payout then is $2.25. But if you lose, what are the odds that you will lose? Well, they're greater. It's 55%. We use multiplication to get your payout, which is going to be $2.75. And then we subtract what you lose from what you win, and what you get is an expected value of minus 0.5. What this means is that for the house in Vegas who's running the craps tables, they know that you're going to lose 5% of the time. 5% of the time, not that you're going to lose 5% of the time, but they're going to make basically 5%. That they will be ahead of you in this because their odds of winning are 55%. And when they do, their value, their expected value, is actually going to be plus 5. Okay. So any number greater than 0 is what we would consider a good bet. That is, given what you have to win and the odds of winning it, it's a good bet. Any number less than 0 is a bad bet. Now you can use this math to calculate the expected value of the lottery, right? You have to know the payout. You have to know the odds of your winning and the odds of your losing and what you lose relative to what you gain. And you can decide, this would be an interesting exercise, the expectation value for your winning the lottery, whether it's worth you buying lottery tickets. So if you're struggling with money, don't buy lottery tickets. Save your money for the important things. Put food on the table first. But you know, if you have discretionary income and you want to spend it on that, you can decide what your expected value is, calculating that. We're not going to calculate it here in this, largely because the odds of your winning the lottery depend on how many people are playing. And notice that the more people who play, the more money there is to win, the greater your win. So it's a very interesting dynamic, and the math there would be very interesting to do with. You would have to take a snapshot, because it's always changing. People are always adding, but you'd have to take a snapshot. If it was like $1 million and it was a dollar per lottery ticket and there were 1 million players, then your odds of winning are 1 in 1 million, and you put up $1 and you win 1 million. Well, do the expected value and you can see whether it's worth playing or not. So okay, let's move on to the final one. Calculating conditional probabilities. This one can get a little bit tricky, and the reason why it can get a little bit tricky is because conditional probabilities by their nature are not just us deciding something simple. Let me start over on this. Here's the question. What are we talking about when it comes to conditional probabilities? Okay. Conditional probabilities basically have a certain form. The form goes like this. If this is true, then that is true, right? That's the basic form of a conditional statement, right? A conditional statement is an if-then statement, okay? And so a conditional probability is one that's structured in that same way. So in terms of, expressed in terms of a conditional probability, let's say, for example, that 1 out of every 10 males at COTC are involved in a car accident while in school. We then want to know what percentage of those who are in a car accident are COTC students. So if 1 out of 10, if 10% of COTC students are involved in a car accident while in school, then what percentage, right, you got my if-then statement, if 1 out of 10, if 10% of male COTC students are involved in a car accident while in school, then what percentage of those who are in a car accident are COTC students? And what I'm doing on this conditional probability is I'm doing a swap here, okay? And I'm switching out the two parts of the conditional, the if-then. The percentage of males COTC students and then the percentage of those involved in car accidents. So let's try another example. I'm sure at this point this is clear as mud. So let me give you another example just of what we're talking about. Let's say that we know that 90% of people who test positive for HIV are in fact HIV positive. Okay? Let's say that there's a 10% failure rate in the test, right? That it gives a false positive 10% of the time. Okay? But 90% of the people who test positive are HIV positive. If that's true, one of the things we might want to know is then what we call the converse, is what percentage of HIV positive people will test positive. Okay? Go back to our prior example. If 10% of male COTC students are involved in a car accident while they're in school, then we might want to know what percentage of car accidents are COTC males. It's not going to be 10%. Likewise, if 90% of the people who test positive for HIV are HIV positive, that is, there's a 10%, the test fails 10% of the time, we might also want to know, translating that the other way, what percentage of HIV positive people are going to test positive. It's not going to be 90%. Here's another one. There are statistics that show that of drivers involved in car crashes, fatal car crashes, 40% are under the age of 26. So 40% of those involved in a fatal car crash are under 26 years old. Well, let's reverse that. If you're 26 years old, then what are the odds that you're going to be involved in a fatal car crash? Here's a hint. It's not 40%. You can't reason that way. That's a bad form of reasoning when we're doing that. So let's look at this. If a certain percentage of X's are Y's, okay, that will not mean that the same percentage of y's are x's. So this, I'm trying to put it in more of a formal form so you can see my switching of the two things. If a certain percentage of a's are b's, that will not imply that that same percentage of b's are a's. You can't swap them like that. Okay? This is a common mistake people make. For example, people will think that if 40% of drivers involved in car accidents are under 26 years old, fatal car crashes are under 26 years old, they think that if you're under 26, you've got a 40% chance of being in a fatal car crash. That's a mistake in reasoning, and we're not doing the probabilities correctly. To determine the percentage of y's that are x's, so if we know the percentage of x's that are y's, or a's that are b's, and we want to determine the percentage of b's that are a's, or y's that are x's, we need to calculate what we call a conditional probability. So that's what this section is about. So how do we do that? Well, the key here is to convert the question to one about proportions to do this. You can't just swap it, and the easiest way to translate it is to turn it into a conversation about proportions. Now, what do we already know? Well, we already know the proportion or the percentage of a's that are b's or x's that are y's, right? We know the percentage of people involved in fatal car crashes that are under 26, okay? That we already know. What do we need to know? Well, if we're going to calculate the percentage of y's that are x's or b's that are a's, I have to know what percentage, or how many, I should say, a's there are per 1,000, let's say, or how many x's there are, right, of the first thing there are per 1,000. And I need to know the percentage of non-x's that are y's. That is, for example, the percentage of drivers that are not in fatal car crashes. If I know that 40% of drivers in fatal car crashes are under 26, one of the interesting things to ask is, yeah, but what percentage of the people as a whole are not in fatal car crashes? What percent of drivers are not in a fatal car crash? A big number of those are going to be people under 26 years old. Okay, so that's kind of what's skewing our data here, by the way. So anyways, I'm repealing something from chapter 8, which we're not covering here, but there are fallacies associated with each of these. If you overlook the first thing you need to know and the second thing, but since we haven't talked about those fallacies, I'm actually going to leave that out of this conversation. So in calculating conditional probabilities, then, let's work with an example. Let's say that we learned that 18% of the people who had flu shots in your town got the flu. So 18% of the people in Newark who got flu shots got the flu, which happens to me, it seems, quite frequently, right? Every time I get the flu shot, I feel like I get the flu. Whenever I don't get a flu shot, I feel like I don't get the flu. But, you know, that's sort of anecdotal. But let's say that we have a hard statistic, and we know that that's true, actually, of 18% of the people who have the flu shot, they get the flu. Then what's the probability of someone who had the flu that they got the flu shot? Again, it's not going to be 18%. Now notice what we've done. We were talking about percentage who had flu shots and percentage that got flu. So it was flu shots and then flu. Now we're wondering what is the probability, or what's the percentage of people who have the flu who had flu shots. So we're swapping the two. B becomes A and A becomes B. Okay? So to relate this then to the previous slide, the X's are the people who had flu shots and Y's are people who got the flu. And what we want to know is how many people per 1,000 had flu shots and how many people did not have the flu shot. You need both of those points of information. From this information, then, we can calculate the proportion of people who got the shots who also got the flu. Okay? So let's check out the next slide. Conditional probabilities continued. So let's say we learn that 100 out of every 1,000 people had flu shots. Okay? So the number we're working with here is 100 out of 1,000 got a flu shot. Now keep 1,000 in mind because that's going to be a good round number for us to work with. That's why we use the 1,000 for a particular reason here, because it's easy to round up and down. Okay. So if we had 1,000 and out of every 1,000, 100 get a flu shot. Okay. Now, by the way, that's basically what percentage of the people overall? It's 10%. Okay. So 10% got a flu shot, and 18% of that, we knew that 18% of them got the flu. Sorry, I was reading flu shot. Of that 100, 18% of them got the flu. I thought it was saying 18% had a flu shot. I had to stop for a second and make sure I was reading that right. That's what happens. You get old and your eyes don't work very well. I wanted to make sure I was reading that right. We knew that 18% of them got the flu shot. Then that's going to be a total of 18 people. Out of 1,000, 100 will have had flu shots, and of those, 18 will have had the flu of that 100. Okay. Now, let's also say that we learned that 24% of those 900 people who did not have flu shots, keep in mind, right? We have to know the number of people who did not have flu shots, and if out of 1,000, 100 had flu shots, then 900 didn't. Now we want to know the percentage of people who didn't have flu shots that still got the flu, right? We know that 18% of the people who did have the flu shot got the flu, but we need to know how many of the 900 who didn't have flu shots got the flu. And let's say we know that that's 24%. That's going to give us a number of about 216. Okay? So now, here's what we have to do, or here's what we have. 18% of 100 people who had the flu shot got the flu. 18. 24% of the remaining 900 who did not get the flu shot got the flu. That's 216. Everybody with me? So out of the 234 people who got the flu, whether or not they got the flu shot, right? That's 216 plus 18. Of the 234 people who got the flu, 18 got the shots, which is 7%. So what happens here is, and this is just an example, that when we say that 18% of the people who got the flu shot got the flu, that doesn't mean that 18% of the people who had the flu had the shot. Really, it's 7% of the people who had the flu had the shot. Just because, here's the point of this whole lesson and the real thing to keep in mind. If I know that a certain percentage of A's are B's, that doesn't mean that that same percentage of B's are A's. We can't swap them. In order to determine that swap, we need to know those two additional points and then do the math. But this is how to calculate that, okay? All right, this is one of our lengthier lessons, so I'm going to go ahead and end it. If you have questions, of course, let me know. Otherwise, consult your book or do what you need to do. All right?